In this video, we're going to take a look at colligative properties of solutions, the effects on vapor pressure, freezing point, and boiling point. So a colligative property is any property that is changed on a liquid as it is dissolving particles in and becoming a solution, and then as more particles are dissolved, the more that property changes. It doesn't matter what the particle is that's being dissolved in, whether it's molecular or ionic, or its molar mass, or the density of it. It's just as those particles dissolve in, the properties of that liquid change as it becomes a solution. So again, the three important ones we're going to look at are vapor pressure lowering, boiling point elevation, and freezing point depression. There's that one, osmotic pressure, but we're not going to look at that. So vapor pressure lowering happens because as particles are dissolved in, those non-volatile particles that are dissolved makes that solution now less volatile. So you have less particles that are escaping to become vapor, therefore lowering the amount of particles pushing down on the surface of that liquid, lowering the vapor pressure on that liquid. And again, that's because as those particles dissolve in, looking at maybe at water, as those water molecules are attracted to that non-volatile solute, and they create that kind of shell around that non-volatile solute. Now they're kind of holding them together, enhancing that kind of bonding going on between those different molecules, and therefore makes it much more difficult for those particles to jump off to become a vapor. And if you have less vapor particles pushing down the surface of the liquid, then therefore you have less vapor pressure. So again, that vapor pressure is going to get lowered, especially with ionic compounds, because when those ionic compounds go into solution, they dissociate. So in like sodium chloride's case, where it's going to dissociate into a sodium ion and a chloride ion, you're actually getting two particles for every one that goes in, and it has a much greater effect on how the vapor pressure is lowered. Sugar molecules, the other side, being molecular, they break apart just molecule by molecule. You're not getting extra particles going to solution, so it's a 1-to-1 ratio, not having as great an effect on the vapor pressure. So one mole of salt will do twice the amount of work on the vapor pressure as that sugar would, again, because it's going to dissociate into its ions, giving us two particles for every mole that goes in, as opposed to one particle for every mole that goes in. So you'd be getting 12.04 times 10 to the 23rd ions, as opposed to the 6.02 times 10 to the 23rd molecules of sugar that would be dissolved in. When we dissolve particles into a liquid and we try to freeze it, the freezing point gets depressed, it goes down. The reason for this is as particles get cooled down, they want to start to crystallize. If it's a pure substance, they have a fixed way in which they will crystallize and come together. But now by adding in these particles that are going to interfere with how that crystallization can happen, it makes it much more difficult for them to make that nice orderly pattern in which they come together and crystallize and make a solid. So therefore, they need to get slowed down even more to get to the point where they can now become some sort of stable crystalline structure. And so that difference between where it normally freezes to where now it will freeze is called freezing point depression. We can figure out the amount of the depression of the freezing point because it is, again, proportional to the amount of particles that are dissolved in. It doesn't matter what that substance is, whether it was sugar or salt or magnesium chloride, everything has the same effect, particle-based, on how much the freezing point will be depressed. In water's case, we see it depress 1.86 degrees Celsius for every molal. For every 1 mole of particles over the kilogram of solvent, then we see their freezing point lowers 1.86 degrees Celsius. That's why in the wintertime in New England, where it snows a lot, we put salt on the road, because maybe at 32 degrees Celsius, where it would be freezing normally pure water, by adding that salt in, maybe we can lower the freezing point down to like 18 degrees. And now all of a sudden, where it's 20 degrees out, if the freezing point, or which also happens to be the melting point, is 18 degrees, at 20 degrees now, it would be a liquid, and that's why it is now no longer ice, it's water. We wash away and keep our streets from being too dangerous. So the boiling point kind of relates to the vapor pressure, because we know that when a liquid boils, the vapor pressure equals the external or atmospheric pressure. So if I've lowered the vapor pressure, now it's going to change the boiling point. And by having a lower vapor pressure, it means I need to heat up that liquid even more to get those particles moving even faster to get that vapor pressure back up. So we see an increase in the boiling point because we need to increase our vapor pressure after adding in that non-volatile solute. And so that difference between the temperature in which it originally boiled to when it now boils is again called the boiling point elevation, since it's increased. And just like the freezing point, there's a fixed amount that it changes as you dissolve particles in it. It doesn't matter, again, what those particles are, if it's molecular or ionic, it just matters of how many particles are going into solution. And we see a change of 0.512 degrees Celsius for every mole of particles that are dissolved in. So not as exciting as how much the freezing point changes, but still a significant amount. Again, as you get to greater and greater concentrations, it's really going to affect how much the boiling point will be elevated.